Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most curious, most quietly powerful mysteries the universe has to offer. Black holes. Not monsters, not voids, but something much more subtle and far more poetic. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into black holes together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. So, what is a black hole? You might picture a swirling drain, a dark tornado in space, or maybe a violent pit pulling in stars like pebbles. These aren't entirely wrong, but they're not quite right either. A black hole isn't really a hole. There's no tunnel, no bottom, no place to fall through. Instead, a black hole is a place where space-time curves so deeply that it becomes, in a way, a kind of pause, a silence in the rhythm of the universe, a place where the usual rules begin to bend. To understand one, you don't have to be an astrophysicist. You just need to picture something very massive and very quiet. Imagine, if you will, a campfire at night. It burns bright, warming everything around it. That fire is like a star, hot, radiant, generous. Now imagine that the fire has used up all its wood. The light dims, the warmth fades. What remains is a dense ember, small and glowing. But what if that ember were to collapse under its own weight? Not just shrink, but keep falling inward, folding space and time around it like a heavy blanket. That's how a black hole begins. Most black holes form from dying stars. Not just any stars, but the heavy ones, the cosmic giants that burn bright and die young. When these stars exhaust their fuel, they lose the fight against their own gravity. Without the outward push of fusion to hold them up, they collapse inward in a final act of surrender. And if the core is massive enough, beyond about 3 times the mass of our Sun, it doesn't stop. It doesn't form a neutron star. It falls further still, all the way down to something we can't quite describe. A place where the laws of physics, as we know them, begin to blur. The result is what we call a stellar mass black hole. Small in cosmic terms, perhaps the size of a city, but with the mass of several suns. Imagine something invisible, utterly dark and yet heavier than anything nearby. That's where the poetry begins, because black holes don't scream, they don't flash, they don't chase, they wait, patient, still, curving space and time so gently, so fully, that even light cannot leave their embrace. You may have heard the term event horizon. It sounds like something out of science fiction, but it's quite real. And it's the boundary that defines a black hole. Not a wall, not a surface, but a line. A one-way door in the fabric of space-time. Cross it, and return is no longer possible. Not for light, not for time, not even for meaning, as we usually understand it. The event horizon is the edge of the unknowable. But here's the curious thing. If you were floating near a black hole, far enough not to be pulled in, you wouldn't see a monster. You wouldn't hear anything strange. You might not even realise what you're near. Because black holes, despite all the dramatic depictions, are not violent by default. They're not cosmic vacuum cleaners sucking up everything in sight. In fact, if you replaced our Sun with a black hole of the same mass, Earth's orbit wouldn't change at all. It would still go around the same path, just in the dark. They are objects of gravity, that's all, but gravity, when deep enough, becomes mysterious. It begins to pull on more than just matter. It pulls on light, on time, on the very geometry of the universe, And so black holes became more than just cosmic leftovers. They became riddles. Not the loud kind, but the kind that hum quietly in the background of everything we know. The kind that, once you notice them, you can't quite stop thinking about. Physicist John Archibald Wheeler, who helped popularise the term black hole, once said that they were the most perfect macroscopic objects in the universe. Perfect in the sense that they are completely defined by just three things: their mass, their spin, and their electric charge. No surface, no colour, no texture, nothing else remains. A star, full of layers and fusion and identity, collapses and becomes just a number. It's a strange kind of transformation, a vanishing almost. A reminder that the universe can take something complex and make it simple, or seem simple. Because what lies beneath the surface, if there even is a surface, is still one of the great mysteries of physics. So tonight, we'll explore that mystery, gently. Not all at once, but like walking into a forest at dusk, one quiet step at a time. We'll look at how black holes bend time, how they merge with one another, and what echoes they leave behind. We'll visit the edges of space and peer into the soft shadows of infinity. And when we reach the end, we may still not know what a black hole is in the deeper sense, but we'll have felt just for a while what it's like to listen to the silence between the stars. And that's not nothing. To understand black holes, we must begin with life. Not ours exactly, but the lives of stars. These are the true ancestors of black holes. They are born, they shine, and eventually they fall. And yet, even in their final breath, they create something new. Most stars live quiet lives. They are sustained by a delicate balance, a tug of war between gravity pulling in and nuclear fusion pushing out. In the core of a star, hydrogen atoms are fused into helium, releasing enormous amounts of energy. This energy radiates outward, creating the light that warms planets, powers photosynthesis, and guides travellers at sea. But more importantly, that light pushes back. It holds gravity at bay. This balance can last for billions of years, but nothing lasts forever. As the star exhausts its hydrogen fuel, it begins to burn heavier elements, helium, then carbon, then oxygen, each new stage shorter and more desperate than the last. Eventually the core reaches iron, and here the star faces a fatal problem. Fusing iron doesn't produce energy, it consumes it. Without that outward push, gravity wins, and it doesn't win slowly. In a matter of seconds the star collapses inward. The outer layers fall toward the core, slam into it, and rebound in a shockwave so violent that it tears the star apart. This is a supernova, a stellar explosion that can outshine an entire galaxy for a brief, terrible moment. The outer layers are flung into space, scattering the heavy elements forged in the star's heart across the cosmos. Gold, calcium, iron, even the oxygen you're breathing right now. These are supernova gifts, scattered seeds from dying stars. But what about the core? If the core is small enough, it will settle into a neutron star, a strange object made almost entirely of neutrons, packed so tightly that a teaspoon of it would weigh billions of tons. But if the core is more massive, typically more than 2 or 3 times the mass of our Sun, it doesn't stop collapsing. No force we currently know can hold it up. It keeps falling, inward, relentlessly. And this is where the black hole begins. There is no bang, no flash. The collapse happens silently, hidden behind its own gravity. The matter is compressed not just into a sphere or a point, but into something our equations can describe but not fully explain. The mass remains, the gravity remains. But the details, what that matter was, what structure it had, are lost beyond the event horizon. A star that once roared with fire becomes a region of space defined only by what it left behind, its mass, its spin, and possibly its electric charge. What's left is incredibly small in size, but vast in presence. A black hole only 10 times the mass of the Sun could fit within the width of a city, and yet near it space would stretch and time would slow, like taffy warmed in the hands of gravity itself. The stronger the gravity, the slower the time, and inside the event horizon, time doesn't just slow, it points inward. The future leads inevitably toward the centre. It's hard to picture, isn't it? We're used to thinking of space as something you move through, and time as something that flows forward like a river. But inside a black hole, those rules are rearranged. Time becomes space, and space becomes time. What once was freedom becomes inevitability. But all of this begins with a quiet death. It's strange to think that the universe's most powerful gravitational objects are born from stars that simply ran out of options, that the most extreme environments we know, where physics itself begins to bend, are the result of stars doing what stars always do: shine, age, and end. There's something comforting in that. Even cataclysm, even collapse follows a rhythm. Black holes, at least the smaller ones, the ones born from collapsing stars, are not anomalies. They're common. The Milky Way alone likely contains tens of millions of them, scattered invisibly between the stars. Most are unseen, drifting through the galaxy like ghosts, betraying their presence only when something comes too close, when gas falls inward and begins to glow, or when another star wobbles near them. They are not exotic outliers. They are part of the story, and the story doesn't end with stellar mass black holes. If these are the pebbles, then farther out in the cosmic pond are the boulders, the supermassive black holes, millions to billions of times the mass of our Sun. But those are for another session. For now, we remain with the ones we understand best, those born in fire and finished in silence. There's a quiet irony here. A star is a blazing engine of light, but a black hole is the absence of it. The star gives, the black hole keeps. The star radiates into the universe. The black hole folds the universe inward. One reveals, the other conceals, and yet both are part of the same cycle. One leads to the other. They are not enemies. They are partners in the long arc of cosmic transformation. So as you lie there, listening gently, perhaps breathing a little slower now, you can imagine a sky not just of stars, but of endings, of stars that have already passed through their brightest days and now rest, invisibly as curves in space-time. Not gone, just changed. Still there, still shaping the universe in their quiet way. And as we drift forward in this journey, we'll begin to see how these silent shapes, born from death, continue to affect everything around them. They do not fade, they do not disappear, they stay, and they wait. Before we can understand why black holes curve time, trap light, or bend the very logic of space itself, we need to sit quietly with the idea of gravity. Not the gravity of textbooks, the kind that appears as an invisible arrow in diagrams, but something more intimate, more graceful. Let's take a slow step back in time and reimagine what gravity might mean, not just as a force, but as a shape. Most of us first met gravity through a falling apple. That simple image, so famous it's practically myth, tells the story of Isaac Newton watching an apple drop from a tree and asking the question that would shape centuries: why does it fall? In Newton's view, gravity was a force, an attraction between any two objects with mass. The apple is pulled toward the Earth, the moon is pulled toward the Earth too, but sideways enough to keep missing, which is why it orbits. It's a lovely, intuitive model, and for a long time it was enough. But the story didn't end there. In the early 20th century, Albert Einstein began to see gravity differently. He imagined space and time not as separate entities, but as threads of the same fabric, woven together into something flexible, something that could stretch and curve, something that wasn't just a backdrop for events, but a player in the story. Einstein's insight was as gentle as it was radical. Gravity isn't a pull, It's a curve. Imagine, if you will, a stretched sheet of soft rubber, smooth and flat. Now place a heavy ball in the centre. The sheet dips, not because anything is pulling it down, but because the weight reshapes the surface. Now take a smaller ball and roll it across the sheet. It doesn't move in a straight line, it curves inward, following the dip. Not because it's being pulled, but because that's simply the straightest path in a curved world. That's what gravity is, in Einstein's view. Mass tells space-time how to curve. Curved space-time tells matter how to move. There's no invisible force reaching out. There's just geometry. And we, all of us, are always falling. Even when we feel like we're standing still, we're held in a gentle arc of motion by the shape of the Earth's presence in space-time. This sounds abstract, but it's not far from daily life. Consider a satellite orbiting the Earth. In Newton's world, it's being pulled toward the planet. In Einstein's world, it's simply following the straightest possible line in a curved environment. Just like the small ball on the rubber sheet, it's not doing anything strange. It's just travelling a path reshaped by the presence of mass. Black holes take this idea to its quiet extreme. A black hole is not just a massive object. It is mass concentrated so tightly, so deeply, that the curve becomes complete. The dip in the sheet no longer has a bottom. It becomes a funnel that narrows without end. Space itself stretches toward the centre. Time stretches too. And this is where the poetry begins. Because in a very real sense, objects near a black hole are not being pulled. They are following the only available paths. The curves of space-time are so strong that even light, which normally moves unbent and unbroken, begins to twist and spiral, and at a certain distance, the event horizon, even light's last option vanishes. It cannot climb back out. We sometimes call this a gravitational trap, but that metaphor misses the gentleness of it. There is no resistance, no clutching. The object that falls in doesn't feel pain. It moves, as it always has. Just now, the rules have shifted. The Earth curves space-time. The Sun curves it more. But a black hole, especially a dense stellar mass black hole, creates a curve so sharp, so smooth and complete that it becomes not just a place in space, but a condition of space. It doesn't pull things in. It simply allows no path that leads out. This idea, gravity as geometry, also explains why time changes near a black hole. If time is part of space-time and space-time is curved, then time itself must curve. Clocks slow near massive objects, not because they're broken, but because time stretches. A second near a black hole is longer than a second far away. Not metaphorically, literally. Time itself becomes more patient. Einstein's predictions about this were bold, but they've been tested and confirmed again and again. In 1976, a small experiment aboard a rocket showed that time really does slow in gravity. The GPS system in your phone needs to account for it. Even the top of a skyscraper ticks slightly faster than the lobby below. These are tiny effects near Earth, but near a black hole they grow. If you sat just outside the event horizon, you might watch the universe race ahead. Stars live and die, galaxies drift, and yet for you, moments pass slowly, calmly, as if time itself has taken a breath. Gravity is not violence. It is not urgency. It is structure, shape. It is the memory of mass whispering to space-time, bend ever so slightly, and let things fall the way they must. In this way, black holes are not freaks of nature. They are in fact the purest expression of gravity, the fullest possible curve, the final destination of mass that has nowhere else to go. So when we speak of black holes, let's speak gently. Let's not imagine them as hungry mouths or snarling beasts. Let's imagine them as folds in the universe, soft, complete, and inescapable. Not angry, just inevitable. And so, as we move toward the horizon in the next part of our journey, remember this. The black hole is not pulling us. We are simply following the path it has written in the fabric of everything, and that path is very smooth. There is a boundary in the universe that marks the edge not of a thing, but of a knowing. It is not made of matter, not painted in colour, not stitched together by light, and yet it is real, measurably so. This is the event horizon, the quiet edge of a black hole, where space folds inward and time slows to almost nothing. From far away, it seems like nothing much, just a shadow, a darker patch of sky. You could point a telescope in its direction and still see only the glow of stars and the gentle fog of interstellar dust. But buried in that space, silent and still, is a border with peculiar properties. You cannot see it directly, but you can feel its effect, like the hush before a snowfall, like the moment just before sleep. The event horizon announces itself not with presence, but with absence. Let us imagine drifting toward it. You're in a small spacecraft, silent, stable, no windows, no hum of engines. You're approaching a black hole slowly, carefully, not falling, but floating. As you near the horizon, you look out, not to see, but to measure. You shine a beam of light forward toward the curve ahead, but the beam stretches, redshifts. The light loses energy, drawn long and lazy by the gravity it fights against, and then it fades, not into darkness, but into nothing at all, not because the light is gone, but because it cannot return. This is the essence of the event horizon. It is not a wall, not a barrier. It is a point beyond which escape is no longer possible. Once crossed, no signal, no particle, no whisper of light can ever come back. It is a one-way threshold, and yet it has no physical edge. If you were falling, you would feel no sudden jolt, no crunch, no ripple in your ship. You would pass through it, as if through air. But the universe would lose track of you forever. From the outside, it looks even stranger. If someone were watching you fall toward the black hole, safely orbiting at a distance, they would see you slow, not just figuratively, but literally. Your movements would grow sluggish, your signals would stretch into radio silence. Your image, red-shifted and dim, would seem to hover at the edge of the black hole, frozen in place, even as, in your own frame of experience, you continue to fall. This is because time near the event horizon is not just distorted, it is reoriented. For the person outside, time marches on as always, but for you, near the horizon, time has stretched. 1 second becomes 10, 10 become 1,000, and eventually all forward motion, at least from the outside perspective, stops. The event horizon is not just the edge of a black hole, it is the edge of what the universe can remember. This strange divide is more than poetic, it is physical, it is measurable, and it is one of the most profound predictions of Einstein's general relativity, that gravity can alter the shape of time itself. The deeper you fall into a gravitational well, the slower your clock ticks, and at the event horizon, that slowness becomes infinite. Time, in a sense, bends so sharply that it no longer flows outward at all. It curls in on itself, like a fern frond or the edge of a wave caught in stillness. But again, this is all from the perspective of the outside. For the person falling in, time feels normal. They do not feel slow, they do not freeze. Their watch ticks forward as always. What changes is not the experience of time, but the availability of paths. The closer they get to the centre, the fewer directions remain. Space narrows, time narrows, and eventually all lines point inward. One could say the event horizon is where choice begins to fade. You cannot turn around. You cannot hover. You cannot call out. Even the idea of direction begins to lose meaning. The geometry of space-time no longer allows for escape routes. It is not hostility. It is not punishment. It is simply how space-time behaves in the presence of such deep curvature. You might think this sounds terrifying. But many physicists describe the event horizon not with fear, but with wonder. It is a perfect surface, flawless, symmetrical. It absorbs everything and emits nothing. And yet, according to Stephen Hawking and others, it may not be entirely mute. Over unimaginable spans of time, it may release a soft quantum whisper, what we call Hawking radiation. But that is for later in our story. For now, the event horizon is quiet, and in that quiet is something philosophical. It reminds us that there are limits, not just to vision or measurement, but to knowledge itself. There are things we can infer, simulate, even imagine, but never confirm. The event horizon is a line not just in physics, but in thought. And so, we might sit with it for a moment. Imagine the edge of a world where light no longer returns. A place where clocks stop ticking from the outside but still beat quietly within. A place that holds stories we cannot retrieve. It is not chaos. It is not noise. It is an eloquent silence. A kind of cosmic kindness, perhaps, that spares us from seeing too deeply into endings. The event horizon is the universe's soft-spoken boundary. It doesn't forbid entry. It simply doesn't allow exit. It lets things pass and then forgets them, gently, without resistance. And in that forgetting, perhaps, there is a kind of peace. We've spoken of the event horizon, the place where light can no longer return, where time slows to a crawl, and where the universe's sense of direction begins to dissolve. But beyond that boundary, deeper still, there lies a point, or rather, something that behaves like a point but evades all our usual definitions. It is known simply as the Singularity, a word that suggests precision, but hides nothing less than the collapse of everything we understand. If the event horizon is a silence, then the Singularity is what that silence encircles. Let's begin gently. What do we mean when we say singularity? In mathematics, a singularity is a place where equations fail, where dividing by zero causes the numbers to spiral out of control. In physics, it's much the same, a point at which the known laws stop producing usable answers, where values like density, temperature and gravity approach infinity. And in the context of black holes, the singularity is the centre, the place toward which all paths within the event horizon inevitably lead. But is it a real place, a physical object, or just a signpost that marks the limits of our knowledge? According to general relativity, when a massive star collapses into a black hole, its mass continues to shrink down into an ever smaller region. Without any known force to resist this collapse, the matter compresses to a point of zero volume and infinite density. This is the singularity, a single location where the curvature of space-time becomes infinite, where all the mass of the black hole is concentrated, where space no longer has dimensions as we know them, and time no longer flows in any direction that makes sense to us. But here's the problem. Infinities are not physical. They are red flags. They tell us something has gone wrong, not in the universe necessarily, but in the tools we're using to describe it. This is where physics, usually so confident, so precise, begins to mumble. General relativity has been tested in countless ways and has always passed with elegance and accuracy. But it is a classical theory. It does not include quantum mechanics, the theory that governs the tiniest scales of particles, probability and uncertainty. And at the singularity, where gravity is strong and distances become minuscule, we need both. We need a theory of quantum gravity, something we don't yet possess. So instead of a definitive answer, we find ourselves in a cloud of possibilities. Some physicists believe the singularity is real, that it truly is a point of infinite density. Others suspect that the laws of quantum mechanics will smear out the singularity into something more manageable, a loop, a shell, a fuzzball, perhaps even a tangle of strings. There are ideas that suggest the singularity might be a bridge to another region of space, or even to another universe. These are not wild guesses. They are careful extrapolations from incomplete maps. But they remain unconfirmed, and so we must tread carefully. We do not know what lies at the heart of a black hole. We only know that our current theories are not enough. The singularity is not just a place. It is a philosophical reminder that even in a universe governed by elegant equations and testable laws, there are places where our understanding fades. Places where we can calculate the edge, but not what lies beyond. There is beauty in that uncertainty. You might think of the singularity as the period at the end of a sentence the universe hasn't finished writing, or as the pupil of the cosmic eye, dark not because it is empty, but because it absorbs everything that reaches it. Not destructive, but hidden. Not chaotic, but silent. If the event horizon is the boundary of memory, then the singularity is the secret the universe keeps even from itself. We cannot see it. We cannot touch it. But we can feel the need for its explanation. This is what drives theoretical physicists to search for a deeper theory. Something that unites gravity and quantum mechanics. Something that works at all scales, from the dance of galaxies to the jitter of subatomic particles. They call it the theory of everything. And at the centre of that search, like a black pearl in the centre of a storm, is the singularity. Some candidates exist. String theory suggests that particles are not points, but tiny vibrating loops of energy, whose harmonics create mass and force. In this model, spacetime might be more than four-dimensional. It might have curled up dimensions too small to detect. If this is true, the singularity could be something spread across those hidden spaces, not concentrated in a single point. Loop quantum gravity, another idea, treats space itself as a kind of quantum fabric, woven not from continuous lines but from tiny discrete chunks, like atoms of geometry. In this model, the singularity might be avoided entirely. Instead of falling into a point, matter might bounce or dissolve into the quantum foam that makes up the very texture of space. These theories are elegant. They are promising, but they are not complete. And so, the singularity remains, not as a known thing, but as a placeholder. A soft silence in the equations, a blank circle on the map, labelled not with monsters but with possibility. What we do know is that any path inside the event horizon leads toward it. Just as gravity bends light and space, it bends destiny. And in that bending we're reminded, the universe is not always loud in its mysteries. Sometimes it hides them inside perfect stillness. So tonight, as we continue our quiet exploration, we do not try to solve the singularity. We simply let it exist. We let it remind us that there are questions worth asking even when answers are far away. We let it be a point not of fear, but of humility, because somewhere, deep inside the darkness, lies a truth we haven't yet learned to name. By now, black holes might seem like ghost stories told in the language of physics, places where time distorts, light vanishes, and the fabric of the universe curves so tightly it folds into silence. And yet, despite all their mysteries, black holes are not monsters. They are not the villains of the cosmos, nor are they unnatural intrusions in an otherwise orderly universe. In truth, black holes are among the most orderly things we know. And though their names evoke emptiness, they are anything but empty. They're not vacuums, they're not violent by default, and they are certainly not out to devour everything in sight. Let's clear the air with a thought experiment. Imagine, if you will, that our sun, the warm glowing heart of our solar system, were to magically be replaced by a black hole of exactly the same mass. A strange event, to be sure, but let's set aside the physical improbability and consider only the gravitational effect. What would happen to Earth? Would we be sucked in, spiraled down like water in a drain, pulled instantly into the darkness? The answer is, nothing would change, at least not gravitationally. Earth would continue on its orbit, circling the new black hole just as it had circled the Sun. It would grow very cold, of course, without sunlight, but gravitationally it would feel no difference. That's because black holes don't pull with any more strength than any other object of the same mass. Their gravity only becomes extreme when you get very close. It's not that they exert more pull, it's that you can get closer to their mass than you ever could with a star, simply because they're so compact. This compactness is key. A black hole doesn't radiate light or heat in the way stars do. It doesn't push away matter with solar wind or stir up dust with magnetic fields. It simply curves space-time quietly, deeply. Things that come too close, too fast or at the wrong angle can fall in. But for the most part, objects can orbit around black holes safely, just like planets orbit stars. In fact, many black holes are entirely invisible unless they interact with their surroundings. A lone black hole wandering through the galaxy may go unnoticed forever, leaving behind no trace except the slight wobbles it induces in any star it passes near. We only detect them when they have companions, when they are part of binary systems or surrounded by matter that glows as it falls inward. Otherwise, they are shadows, real, massive, and yet completely silent. And this brings us to one of the most misunderstood features of black holes, the accretion disk. When gas or dust, or an unlucky star, gets too close to a black hole, it doesn't immediately fall in. Instead, it begins to spiral around, forming a thin, hot disk of material orbiting at incredible speeds. Friction in this disk heats the material to extreme temperatures, causing it to glow in X-rays and gamma rays, high-energy light we can detect with space telescopes. It's from these disks that many black holes reveal themselves. The black hole itself emits no light, but the matter around it screams as it falls. Not in sound, of course, but in photons, flashes of energy trying to escape the inevitable. These luminous disks are not signs of destruction, they are signs of process, of transformation. And while they may look chaotic, they follow precise physical laws. The orbits, the spirals, the jets of matter that sometimes burst from the poles of the system, all of it governed by gravity, magnetism, and momentum. Nothing here is supernatural. Nothing is inexplicable. It is simply intense. Some of these black hole systems are even rhythmic. Their light flickers at regular intervals, their emissions pulse like a heartbeat. We can listen to these rhythms with our instruments, translating light into data and data into sound. Some researchers have even created audio from these patterns, revealing a deep, steady hum, a gravitational lullaby that stretches across the cosmos. And still, the idea persists that black holes are dangerous in and of themselves, that they roam the universe like cosmic predators, but they do not hunt, they do not move with hunger, they are not alive, they are not even especially rare. There may be millions of black holes in our galaxy alone, each one formed from the natural death of massive stars, each one following the same physical rules as every other object in the universe. They are not errors, they are not mistakes. In fact, they may be essential. Black holes help shape galaxies, they anchor stars, they stir gas clouds into motion, and may even regulate star formation. In some sense, they provide structure to the otherwise chaotic dance of gravity on a cosmic scale. Without them, the universe might be very different, and perhaps far less hospitable. So if we're to tell the story of black holes honestly, we must include not just their strangeness, but their stability, not just their mystery, but their elegance. They are not anomalies, but solutions, natural outcomes of physics pushed to its most extreme yet still comprehensible. They are not monsters, they are mirrors, reflecting back to us the rules of a universe that is, at its core, deeply patient. And like mirrors, they show us something of ourselves. We too are shaped by gravity, by cycles, by collapse and creation. We too orbit unseen centres. We carry mass, momentum, memory, and like black holes, We are defined not just by what we contain, but by what we affect. So as you close your eyes tonight, if you do, perhaps you can imagine the black hole not as a threat, but as a quiet presence, steady, unmoving, calmly curving the fabric of space around it. A stillness so complete that even time must bow. And in that stillness, perhaps you'll find a little peace. Time feels so steady in our lives. It ticks forward, unchanging second by second, like the rhythm of a distant drum you never quite notice until you stop to listen. We wake, we work, we sleep. The clock spins, the calendar turns. There's comfort in that rhythm, an illusion of permanence, of uniformity. But the truth is, time is more like a river than a metronome. It flows differently depending on where you are, what you're near, and how fast you move. And near a black hole, time doesn't just flow differently. It stretches, it deepens, it changes shape. This idea, strange as it may seem, isn't fantasy. It's a tested truth of Einstein's general relativity. Gravity, that quiet force we've already reimagined as a curvature of space-time, affects not just where you are, but when you are. The stronger the gravity, the slower time passes. Not slower as in it feels longer, but slower as in your watch will tick differently than mine. Your seconds won't match up with someone else's, even if they're only a few kilometers away. Let's start small. If you stand at the base of a mountain and your friend stands at the top, their clock will tick a tiny bit faster than yours. Not by much, fractions of a nanosecond, but enough that we must account for it in GPS satellites. The satellites orbiting Earth, far from its centre, experience weaker gravity than we do down here. Their clocks run faster. If we didn't adjust for that, your phone would lead you astray, slowly but surely. Every time you tried to find your way home, that's gravitational time dilation, and it becomes more dramatic as gravity increases. Now imagine you're floating near a black hole. Not inside it, not yet, but just outside the event horizon, hovering with thrusters gently keeping you from falling in. To someone watching from far away, time for you appears to slow, not metaphorically, not poetically, literally. Your heart beats more slowly. Your thoughts, your words, your actions, all unfold at a crawl, at least to the observer's eyes. But for you, inside your ship, everything feels normal. Your clock ticks like it always has. You don't feel time slowing, you feel fine, steady, alive. But out there, years are passing, decades, perhaps centuries, all while you experience only minutes. And this leads us to a famous thought experiment, the twin paradox. Imagine two identical twins. One remains on Earth. The other boards a spaceship and travels near a black hole. She flies close, just above the event horizon, then returns. When they meet again, the twin who stayed behind has aged far more. Wrinkles, grey hair, a lifetime lived. But the traveller, the one who skimmed near the black hole, has aged only a little. She is younger, not in spirit, but in body. Her time stretched, her life, relative to the rest of the universe, unfolded more slowly. This isn't just a story. This is physics. It has even been tested in miniature. Astronauts aboard the International Space Station experience time slightly differently from people on Earth. Their clocks tick just a bit more slowly due to both their speed and their position in a slightly weaker gravitational field. Not enough to notice, but enough to measure. And so, near a black hole we find time behaving like warm honey. It slows, it thickens, it clings to the moment. If you could somehow hover there, just above the point of no return, you could watch the universe race forward. Galaxies spinning, stars being born and dying, civilizations rising and fading, all while you simply floated, unchanged, in the hush of gravity's deepest well. But no human has ever hovered near a black hole. Not yet. And perhaps not ever. Still, the math allows us to imagine it. The equations describe what would happen, how time would stretch, how you might see the entire future of the universe play out before you in a brilliant and fleeting arc. If only your eyes could capture it. If only your mind could endure the flood of information. There's a stillness to this thought. We often think of black holes as violent, destructive. But what if instead we saw them as slow places, as resting places? Time does not cease within them, it moves inward. But near their edges it becomes patient, gentle. If you ever needed to escape the rush of the cosmos, this would be the place. And yet, there's an irony here. To slow time, you must approach danger. The closer you get to the horizon, the more you risk being pulled past it. The safest place to watch the world slow is also the most dangerous place to be. So black holes offer us a strange trade, the deepest calm, at the edge of the greatest fall. Time, it seems, is not a background rhythm, it is shaped by the mass around us, and black holes, being the densest places in the known universe, shape time more than anything else. They stretch it, bend it, make it behave in ways that defy our daily intuition. And yet, even this strange behaviour follows rules. Rules we can understand, calculate and describe. There's comfort in that. Because it means that even in the deepest curves of space-time, even at the very edge of forever, we are not lost. We are not without pattern. The clocks still tick. The equations still hold. And somewhere, within the strange symphony of mass and time, you are still part of the rhythm. So next time you glance at a clock, when the seconds seem to crawl or fly, remember that time is not a fixed thing. It's a woven thread, and gravity, quiet and constant, pulls gently at its edges. Near a black hole, that thread stretches long. If time slows near a black hole, then light, our most loyal messenger, must also find its path altered. Normally light travels straight. It is unbound, free and impossibly fast. It dances from star to eye, from sunrise to mirror, from candle to window pane. But near a black hole, even light begins to curve, and not just slightly. At a certain distance, it bends so perfectly that it can circle the black hole endlessly, in a path that neither escapes nor falls in. This is the photon sphere, a glowing, ghostly ring, where light becomes a prisoner of its own forward motion. Let's slow this down. Imagine a beam of light passing near a black hole, not too close, but not too far either. It's moving as it always does, at the speed of light, but the space it travels through is no longer flat. The black hole's immense gravity has curved space-time into a bowl, like a lens with no edge. The light isn't pulled, exactly. Instead, it follows the straightest possible path through this curved space, and that path is a circle. It's difficult to picture because it doesn't happen in our daily lives. On Earth, light may refract through glass or bounce off water, but it never orbits. There's nothing heavy enough to bend space-time so sharply. But near a black hole, particularly just outside its event horizon, light can become trapped. It can loop endlessly, like a whisper circling the inside of a bell, never quite fading, never quite escaping. This photon sphere exists only at a very specific radius, about 1.5 times the Schwarzschild radius of the black hole. Any closer, and light will fall in. Any farther, and it will escape outward. But right at that balance point it spins, fragile, perfect, caught in between. But here's the beautiful twist. We never actually see this photon sphere directly. What we do see, when we're lucky, when the instruments are just right, is its echo, its shadow. In 2019, the Event Horizon Telescope captured the first image of a black hole silhouette. It wasn't the black hole itself, of course. You can't photograph something that emits no light. But what we saw was the surrounding glow of the accretion disk, the heated gas spiralling into the void, and in the centre a dark circle. That circle was the black hole's shadow, cast not by the absence of light, but by light trapped in orbit. bending around the void and failing to reach us. The image was blurry, orange, softly haloed like the glow behind a candle seen through frosted glass. But it was real, a photograph of curved space-time, a portrait of gravity so deep that light itself bowed and bent in silence. It's important to understand that the light in that image isn't coming from the black hole. It's coming from matter just outside, glowing as it heats. But some of that light takes incredibly long, twisted paths. Some loops around once or twice, distorted by the gravity well, before escaping toward our telescopes. The result is a kind of optical illusion, where we're seeing not just the matter in front of the black hole, but also the matter behind it, light bent into visibility by the curvature of space. This is gravitational lensing at its most extreme, and the photon sphere is the quiet artist behind the illusion. We can imagine it as a ring of invisible glass, bending light into strange patterns, not because it tries to, but because it must. In that region, the universe's geometry insists on circularity. Paths that should be straight become curved, motion that should be free becomes bound, and light, so often a symbol of escape, of reaching, of movement, is instead caught in place. This strangeness is not limited to photons. Anything moving at or near the speed of light would find itself affected. But light is special because it lets us see, it lets us know, and so, when light is trapped, our knowing becomes trapped too. We can observe the surroundings of a black hole, we can watch stars orbit, we can detect high-energy jets and X-ray flares, but we cannot see within the horizon, and we cannot truly see the photon sphere. We can only infer its presence from the way light behaves, twisting, looping, shimmering like ripples around a drain. There's something hauntingly poetic about that the closest we can come to seeing a black hole is through the paths of photons doomed to orbit it forever. That the brightest image we have of the darkest thing in the universe is drawn by light that never quite escapes. That even light in its speed and clarity can be slowed and shaped, not by anything violent, but by pure geometry. So what does this mean for us, lying here, far from any black hole? It means that even the fastest thing we know, light, has limits. That even the most direct paths can become loops. That sometimes trying to see something too closely means we only ever see its outline. Perhaps that's true of more than just astrophysics. Perhaps it's true of memory, of longing, of the things we try to understand by circling them again and again from a safe distance, hoping for a glimpse, accepting only shadows. And so, the photon sphere becomes not just a region of space-time, it becomes an image, a metaphor, a place where persistence meets futility, where motion meets silence, where even light must pause and stay a while, and perhaps that's enough. There's a curious dissonance when it comes to black holes, a gap between what we see and what is, and nowhere is that dissonance more striking than in the simple act of falling. You might think that if an object, say, a spacecraft or a star, gets too close to a black hole, you'd watch it fall inward, accelerate, cross the event horizon, and disappear. But the truth, or at least the truth from a distance, is far stranger. From the outside, the object never seems to quite arrive. Let's unfold this gently. Imagine a small spaceship approaching a black hole. It's uncrewed, perhaps, guided remotely. You're observing it from a safe orbit far away, your instruments carefully tracking its trajectory. As it nears the event horizon, you notice something peculiar. The ship appears to slow down, not because its engines are firing, but because time itself is stretching. Each moment takes longer to unfold. Its lights begin to fade into red, dimming not because they've failed, but because the wavelength of their light is stretching under the intense gravity. They fall out of visible range. The ship appears to hover, suspended above the black hole's surface. And then, it stops. It freezes. but it hasn't frozen. It hasn't stopped moving. From your distant vantage point, time near the black hole has dilated so dramatically that the ship seems paused, stuck just above the horizon. If you had infinite patience and perfect eyes, you'd still see it there, thousands or millions of years later, still hovering, still falling. This is the illusion of frozen time. From the falling object's point of view, everything proceeds normally. The ship crosses the event horizon without drama. No bumps, no walls, no sharp transition. It falls inward, toward the singularity, carried by the curvature of space-time. The clocks on board tick normally, the instruments hum. The sensors register nothing unusual at the horizon. Time does not freeze. There's no sense of crossing into a forbidden zone. The fall is smooth, unremarkable. It's only from outside that the story changes. This disconnect between what the falling object experiences and what the outside observer sees is not a glitch. It's a natural result of relativity. Time is not a single universal thread. It's personal, local. What you experience depends on where you are and how gravity shapes your path. There's no single truth about the timing of events, only different perspectives, each valid in their own frame, and in the case of a black hole, those perspectives diverge completely. From the outside, the ship never crosses the event horizon. It asymptotically approaches it, slower and dimmer, until it fades into darkness. From within, it crosses and continues inward. Two stories, both true, neither complete. It's strange, isn't it? That reality could contain such contradictions. That something could both happen and from another viewpoint never quite happen at all. But this is the heart of general relativity. Space and time are not fixed. They bend, not only under mass and motion, but under perspective. This has led to philosophical musings over the years. If nothing ever seems to cross the event horizon from the outside, then where do black holes get their mass? If all infalling matter appears frozen just above the surface, does the black hole ever truly consume anything? And if not, what does it mean to say that something has fallen in? These aren't trivial questions. They touch on the very definition of a black hole. Some physicists argue that, practically speaking, we can consider the matter to have fallen in. It's hidden from view, gravitationally part of the black hole, even if we never observe it crossing. Others suggest that, from a strict observational standpoint, we only ever see the horizon thicken, the shadow deepen, but never the fall itself. But in truth, this isn't just about physics. It's about how we perceive change. There are moments in life that feel like this, where something is happening undeniably, and yet from the outside it seems static. A decision, a grief, a transformation. From within, the journey is clear. From without, it's invisible. We freeze, at least in the eyes of others, while deep inside, everything is still moving. The falling object and the watching eye. Two truths, one story. And perhaps the most elegant part of this tale is that black holes do not resist this ambiguity. They require it. Their nature demands that we accept multiple views, that we acknowledge the limits of any one vantage point, that we learn to hold contradiction gently, like a shell with different colours on each side. So when you think of a black hole, don't imagine a violent consumption. Don't picture something sucked in like a noodle through a straw. Imagine instead a stillness, a vanishing not of matter, but of presence. From the outside, the world forgets the falling object. From the inside, the object forgets the world. And maybe that's what it means to cross a boundary no one can see. It's not a crash or a snap. It's a soft divide, a slipping away, a moment where one story ends for someone, but continues for someone else. Just as we, sitting here under our own sky, drift through the fabric of time without fully seeing the threads. Just as light curves, and clocks disagree, and memories fold themselves into different shapes depending on who holds them, so tonight, as you lie in the hush of your own orbit, imagine watching something fall not with fear, but with quiet awe. not as a loss but as a change in language, a motion you can no longer describe but one you know still continues. Because the universe does not end at the edge of what we can see, and neither do we. Before black holes merge in a grand, silent collision, before space-time rings like a bell and observatories catch whispers from across the cosmos, there is a dance. It is a slow, invisible choreography, ancient and patient, unfolding across millions, sometimes billions of years, and in this dance, gravity leads. Picture, if you will, two massive stars, bright and defiant, burning through their fuel in the lonely arms of a galaxy. Perhaps they were born in the same nursery, spun from the same cold cloud of gas and dust. Perhaps they found each other later, drawn together by gravity's quiet persistence. Either way, they become a binary. Two stars bound not by ropes or chains, but by a mutual fall. Each circles the other, tethered by nothing more than curved space and silent inertia. And as time passes, they live out their luminous lives. Each grows old, each dies. Massive stars do not go gently. Their cores collapse, their outer layers explode in supernovae. Brief, brilliant deaths that outshine entire galaxies for a moment. And what remains after such fire? A neutron star, perhaps. Or, if massive enough, a black hole. Now imagine both stars in our binary are massive enough to leave behind black holes. What you have now is a pair of invisible anchors. Two black holes orbiting one another in the dark, circling not with noise or light, but with mass and movement alone. They spiral slowly, at first separated by vast distances, their orbits wide and stable. But with every revolution, something tiny but significant happens. They lose energy, not through friction, not through wind or drag, but through a phenomenon far subtler: gravitational waves. Gravitational waves are ripples in space-time itself. Just as a pebble dropped in a pond creates rings that travel outward, so too do massive objects in motion disturb the fabric of the universe. It's not an analogy, it's what Einstein predicted, that accelerating masses, especially massive ones in tight orbits, should create disturbances in the structure of space-time, waves that move outward at the speed of light, carrying energy away. These waves are unimaginably weak by the time they reach us, but at their source, where two black holes spiral closer and closer, they carry enough energy to affect the system. As the waves escape, they steal just a little bit of orbital energy with them. Not much, but enough. Slowly, over millions of years, this loss causes the orbit to shrink. The black holes move closer, the dance tightens, and yet there is no resistance, no struggle. The partners do not fight the change. They simply follow the path laid out by gravity's quiet persistence. For a long time, nothing appears different. The orbit shrinks, yes, but on human timescales it's imperceptible. The system continues deep in the galaxy, unlit and largely undetectable, until, at some point, after countless silent revolutions, the black holes are close enough that the pace quickens. The dance becomes a spiral. The spiral becomes a rush. And then finally, a plunge. But that final plunge, the actual merger, is just the punctuation mark. The real story is this slow, graceful decay, the long fall, the quiet loss of separation. It's here, in the patient circling, that the beauty of the system lies. A black hole binary isn't just a collision waiting to happen. It's a relationship, a gravitational bond that evolves over cosmic time, shaped by nothing more than the curvature of space-time and the slow exhale of energy into the void. These binaries are rare, but not impossible. In recent years, with instruments like LIGO and Virgo, we've begun to detect their final moments, those last seconds before the merger, when the gravitational waves grow stronger and more frequent. But what we detect is only the end. The beginning, the billion-year dance, is invisible to us for now. All we can do is model it, infer it, imagine it. And perhaps that's enough, because even in imagination, the image is powerful. Two black holes orbiting one another in the dark, silent, steady, bound by nothing but gravity, losing energy not in fire or friction, but in ripples of space-time that spread outward across the cosmos like forgotten footsteps in a soft field of snow. No light, no sound, just motion and time. You might be tempted to think of this as tragic. Two stars that burned brightly, now reduced to featureless voids circling each other in a lifeless ballet. But perhaps there's another way to see it. Not as an ending, but as a rhythm, a continuation. A deep kind of harmony between objects no longer made of matter, but still participating in motion, still affecting the universe, still sending out faint, elegant signals that carry meaning, if only we know how to listen. And listen, we have. It took a century after Einstein predicted them for gravitational waves to be confirmed, but when LIGO first heard one in 2015, a rising chirp from the merger of two black holes over 1 billion light-years away, it was not just a scientific achievement, it was a moment of poetry. The universe had always been ringing. We had finally built ears to hear it. But before the chirp, before the ring down, before the merger, there was this, a long, slow dance, invisible but real. And now, as we move closer to the moment of collision, we carry that stillness with us, because even in their final approach, black holes remind us that not all stories are told in light. Some unfold in curves, in patience, in motion we cannot see, but somehow feel. At the end of their long, invisible courtship, two black holes do not collide. Like boulders, they do not crash or shatter. There is no noise, no shockwave, no flare of light. Instead, there is a deepening, a folding, a seamless merging of two gravitational wells into one, as though the fabric of space-time, tired of being stretched in two places, decides gently to pull them together. The final orbit is fast, so fast it's hard to imagine, just milliseconds long. The two black holes are now separated by a distance only a few times their own diameters, spiralling inward at nearly half the speed of light. Their horizons, those quiet one-way surfaces of no return, begin to bulge and stretch under the influence of each other's gravity. They distort, they twist. They begin to lose their identity as separate objects, becoming not a pair but a process. This is the moment of merger, and yet to call it a moment is misleading. It's not a single point in time, but a brief passage, a transition. For a fraction of a second, space-time becomes deeply, violently curved, but not in a way we can see. There is no brightness, no explosion, just gravity at its most intense, reshaping the structure of the universe in total silence. You might imagine it as two dark oceans meeting, each deep, each still, each powerful. Their surfaces fold together, becoming one body, not with a splash, but with a soft, inexorable pull. A union not of turbulence, but of inevitability. The event horizons coalesce, the singularities merge, and what emerges is a single, larger black hole. Quieter, but heavier, still pulsing with the memory of what just occurred. Outside, if you were watching from a safe and impossibly close distance, you wouldn't see the black holes themselves, but you might detect the gravitational waves, the final, rapid oscillations in space-time that ripple outward from the collision. These waves would carry more energy in a split second than all the stars in the observable universe emit in light during that same time, and yet they would not burn. They would not blind. They would pass through you without resistance, stretching and squeezing space by less than the width of a proton. They are the quietest loudness the universe knows. We sometimes speak of these mergers as cataclysms, but the word feels wrong. Cataclysm suggests chaos, destruction. What happens here is more refined, more pure. It is not a breakdown, but a simplification. The system resolves itself into a single solution, a single horizon, a single future. For the black holes, this is not death, it is continuation. Their individual spins, those slow whirls of twisted space, combine into a new spin. Their masses add together, though not completely. Some portion is radiated away as gravitational waves. The final black hole is a little lighter than the sum of its parts. What is lost is not material, but motion. The energy of the orbit transformed into waves that now travel endlessly outward, bearing witness. And there's something quietly moving in that, even in the dark, even without light, two objects can meet and leave behind a signal. A story, a mark on the universe's memory, not in colour or heat, but in rhythm, in the silent song of gravity. We've begun to hear these songs. LIGO, Virgo and other observatories around the world now listen to the cosmos not with eyes, but with vibration. They measure the stretching of space-time itself, recorded with astonishing precision. And when two black holes merge, the signal is brief but unmistakable. A rising frequency, a sudden chirp, then silence. From those few seconds we can infer everything. The masses of the black holes, the distance from Earth, the energy released, the spin of the remnant. It's as though the universe sings one note, and from its tone we learn the entire symphony. But all that happens after the merger. Right now, in these final milliseconds, the process is at its most intense. The curvature of space-time is at its sharpest. The gravitational waves are at their peak. The two black holes become a blur, a single entity still vibrating with the memory of emotion. It's not a dance anymore, it's a chord resolving, a breath held then exhaled, and then just as suddenly as it began, it's over. There's only one black hole now, quiet again, round again, alone again, but changed. For this new black hole carries with it the history of what came before, not in any visible way, not in scars or cracks, but in spin, in mass, in the tiny measurable kick that may send it drifting through space. It is heavier, it is more complete, and it is part of something larger, the great cosmic cycle of formation, collapse, interaction and merger. This has happened countless times across the universe, and it will happen again. Black holes will continue to find one another, to spiral, to merge, to sing, and we, here on this small spinning world, will continue to listen, not with fear, but with wonder. Because in the end, these collisions are not about destruction. They are about connection, about two things becoming one, about the patterns left behind by what once was two, now folded into the silence of one. And perhaps, in that quiet union, we can find a small reflection of ourselves. After the merger, after the last spiral, the final orbit, the soft collapse of two gravitational giants into one, there is still a sound, not a literal sound, of course, not something you could hear with ears or record with a microphone, but a ringing nonetheless, a subtle vibration in the fabric of space itself. It is the voice of the cosmos adjusting to what just happened, a newborn black hole settling into its new shape, sending out one final echo of what it once was. This moment is called the ring down. Think of a bell. You strike it with a mallet and it vibrates, its metal shell oscillating in a pattern shaped by its size and form. The sound is pure, clear, fading slowly as the bell gives up its energy to the air around it. The black hole does something similar, except here the bell is space-time, and the air through which it rings is the entire universe. In those final milliseconds after the black hole forms, it is not yet perfectly round. The newly merged entity is still vibrating, still a little distorted by the violence of its birth. Its horizon, once two separate surfaces, now one, ripples like the surface of a disturbed pond, and those ripples send out waves, not of water, but of gravity, not in any direction we can see, but in the shape of space and time themselves. The result is a very specific kind of gravitational wave, a pattern that fades quickly but carries information, the final frequency, the decay rate, the last few notes of the black hole's song. It is these notes that scientists study with exquisite care. From them, we can extract the properties of the remnant black hole, its mass, its spin, and whether it truly aligns with our theories of general relativity. It's astonishing, really, that from a signal less than a second long, from a distortion smaller than a proton in detectors kilometers wide, we can hear the death and rebirth of massive stars, that the universe can ring like a musical instrument, and we can, after all this time, tune in. And the pitch of this cosmic ringing is not like any sound you've ever heard. When scientists first converted gravitational wave data into audible sound, they found it wasn't a roar or a crash, but a chirp. A rising tone, sudden and brief. It begins low, ascends rapidly, and vanishes. That chirp represents the final seconds of two black holes spiralling inward, colliding and ringing down. It is the audio translation of curvature, motion, and merging mass. LIGO and Virgo, the great observatories of gravitational waves, are not telescopes in the traditional sense. They don't look at stars. They don't capture light. Instead, they use lasers to measure tiny changes in distance, changes caused by passing gravitational waves stretching and squeezing space. The machinery is delicate beyond belief. The alignment, the silence required, the reduction of all noise except that of the cosmos itself. It's like building a violin that only plays when the universe hums. And in 2015, that violin played for the first time. The wave was faint but clear, a chirp, the final breath of two black holes that had merged over 1 billion years ago. Their waves had travelled across galaxies, through emptiness, through time, until they passed through Earth, and nudged space just enough for us to notice. It was a moment that changed physics, not because it showed something new, but because it confirmed something deeply predicted. Einstein had written the equations a century earlier. The ring down was in the math. But hearing it, actually recording the sound of space-time rearranging itself, was a leap from thought to reality. It was as if the universe had sent us a postcard from an event no eye could see. And these ring downs continue. With every new merger, LIGO and Virgo capture more. Each one is slightly different. Each tells us something new, not just about black holes, but about the universe itself, how it expands, how it curves, what it's made of. The signals give us clues about the strength of gravity, about whether space behaves the same in all directions, about whether the rules we've written on chalkboards for decades still hold true in the dark. But beyond the data, beyond the numbers and the plots, there's something quieter, something more intimate. It's the feeling that somewhere out there, the universe is not just moving, but resonating. That space-time is not a passive stage upon which events unfold, but a living, breathing fabric that can be shaken, stirred, and soothed. That even in the vast silence of the cosmos there is rhythm, and rhythm means memory, because to ring is to remember, to carry the shape of an impact outward, to let it fade slowly, gracefully, to echo what once was. So when you hear that chirp, when you imagine the universe vibrating from a collision no one saw, remember this: you are listening not just to physics, but to history, to a story told in waves and silence, to an event so massive it left its mark on the cosmos itself, and so delicate that only now, with our best instruments and most patient minds, have we begun to hear it. Let it ring softly into your thoughts tonight. After the black holes merge, after space-time rings and quiets, what remains is stillness, but not sameness. The universe has changed. A new black hole sits at the heart of where two once orbited. The wave has passed, the song has faded, but the shape of the cosmos is slightly, forever different. And from that shape, subtle, precise, and deeply mathematical, we learn. This is the moment when science shifts from awe to analysis, not because the awe ends, but because it takes on a new form, one woven with equations, simulations, and measurements that reveal what the ringing remnant has become. The black hole may be silent now, but it has left behind a signature, a pattern in the gravitational waves that tells us not just what happened, but how. To understand what remains after the merger, we must first ask, what is conserved and what is lost? Mass, for one, is not simply added. When two black holes merge, the mass of the resulting black hole is not quite the sum of the two that formed it. A portion of that mass, sometimes several solar masses worth, is carried away as energy in the form of gravitational waves. This isn't speculative, it's measured. From the data gathered by detectors like LIGO, scientists can calculate how much energy left the system during the collision. It's a staggering number. In many cases, more energy is radiated in that final moment than all the stars in the observable universe emit in light over the same period. But the remaining black hole is not just smaller than expected, it's spinning. And the way it spins tells us even more. Black holes, though seemingly simple, are described by only a few fundamental properties: mass, spin, or angular momentum, and electric charge. In most astrophysical contexts, the charge is negligible. But spin, that's where things get interesting. The two pre-merger black holes each had their own spins, their own orientations, their own momentum. When they merged, their spins combined in complex ways. The final black hole's spin depends on both the magnitude and direction of the original spins, as well as the alignment of their orbital motion. If the original black holes were spinning in the same direction as their orbit, the final spin will be strong and smooth. If they were opposed, or tilted, the result may be more chaotic, a black hole wobbling briefly before settling, like a top adjusting itself after a sudden push. These small differences are visible in the gravitational wave signal, especially in the ring-down phase. Scientists decode these variations, comparing the observed waveform to thousands of simulated ones, looking for the best match. And in that match, they find stories. Stories of how the black holes formed, whether they were born together like twins from the same stellar nursery, or captured each other later in the dense chaos of a star cluster. Whether their spins were aligned by a shared origin, or random from a chance encounter. Whether the resulting black hole was kicked, recoiled, by an asymmetric wave emission, sent drifting through space at hundreds or even thousands of kilometers per second. These kicks, though invisible to our eyes, are part of the cosmic ledger. When two black holes merge unevenly, say if one is larger or spinning differently, the emission of gravitational waves can be slightly lopsided. That imbalance creates a kind of recoil, like the kickback from firing a cannon. The new black hole may be sent moving, not fast enough to escape a galaxy, usually, but fast enough to wander. Some might even escape smaller galaxies entirely, becoming intergalactic travellers, massive, invisible, and alone. And yet, even that movement leaves a clue. In the waveforms, in the shape of the ring down, in the way space was stretched and relaxed, is like reading the footprints left after a dancer leaves the floor. Not just where they were, but how they moved, how they turned, how much weight they carried with each step. These measurements aren't just exercises in precision, they test the very foundations of physics. General relativity makes specific predictions about the properties of the final black hole, based on the masses and spins of the initial pair. By comparing our observations to those predictions, we confirm, or challenge, our understanding of gravity at its most extreme. So far, relativity has held firm. Every wave detected, every ring down heard, every spin inferred has matched the theory. No cracks, no deviations. Einstein's equations, written in the early 20th century, continue to guide us through phenomena he could scarcely have imagined detecting directly. But scientists are always watching, always listening. Because one day, one of those mergers might reveal something unexpected. A signal that doesn't match any model, a black hole that shouldn't exist, a ringdown that hints at physics beyond what we know. And even if that day never comes, the precision itself is its own reward. It tells us that we live in a universe that is not only vast but knowable, that even the wildest events, mergers of invisible giants a billion light years away, can leave behind trails we can follow, that the cosmos, for all its silence, is also meticulous, that it writes its stories in waves, in curves, in quiet aftermaths. So what remains after the black holes have merged? A single, spinning, larger black hole, a changed patch of space, a wave that rippled outward and passed through us, a ringdown that sang briefly and faded, a data set on a computer matched to a theory, a moment we caught, measured, understood, and maybe above all the sense that even in the darkest parts of the universe there is order, not just chaos contained, but harmony revealed. To see a black hole is to attempt the impossible. By definition, they do not emit light. They do not reflect, sparkle or shimmer. They offer no colours to the eye, no images to a lens. They are, as far as photons are concerned, a dead end. And yet, we see them. Not directly perhaps, but unmistakably. We see their influence, their outlines, their silent gravity brushing against the world around them. We see the way they bend what isn't them, light, space, time, and in doing so they become visible in absence, seen not by what they are, but by what they change. It begins with motion. At the centre of our galaxy, 26,000 light-years away, stars orbit a point of darkness, not in random patterns, not in lazy spirals, but in tight, fast, precise ellipses. One of them, S2, completes its loop in just 16 years, moving at speeds that seem unreal, over 7,000 kilometres per second at its closest approach. It dances around something that exerts the gravity of 4 million suns, packed into a space no larger than the orbit of Mercury, and yet nothing shines there. No star, no glow, no cluster, just darkness. Invisible, but undeniable. That something is Sagittarius, a star, the supermassive black hole at the heart of the Milky Way. We see it not with eyes, but with logic, with careful measurement. The mass is there. The motion proves it. And the darkness confirms what it must be. Elsewhere, we see black holes by the light of their surroundings. When gas and dust fall inward, they spiral into a glowing disk, the accretion disk, heated to millions of degrees by friction and gravitational compression. The matter itself emits X-rays, radio waves, sometimes even jets of particles blasting out, perpendicular to the disk at near light speed. These outflows ironically make black holes some of the brightest objects in the universe, not from the black holes themselves, but from the frenzied matter on the edge of their hunger. We see these blazing regions in galaxies billions of light years away and call them quasars. They outshine their entire host galaxies, and at their centre, always, lies a black hole. Quiet, massive, organising the storm, but sometimes light bends even before it reaches us. When a black hole passes between us and a distant star or galaxy, its gravity warps spacetime enough to bend the light like a lens. We call this gravitational lensing, and it creates arcs, rings, or magnified images of the background object. It's as though the black hole holds up a curved mirror, not to show its face, but to bend someone else's. From these distortions we infer mass. We measure curvature. We deduce presence. It is one of the most poetic aspects of general relativity, that mass bends space, and space bends light, and light carries the story back to us across time. But of all the images, one changed everything. In 2019, after years of coordination and calibration, scientists with the Event Horizon Telescope unveiled the first direct image of a black hole's shadow. The target was M87 star, a supermassive black hole at the heart of a galaxy 55 million light-years away. The image was not crisp, it was not detailed, but it was real. A ring of fire surrounding a dark centre, the ring glowing with the light of infalling gas. The shadow, cast not by the black hole itself, but by the photon sphere. The region where light orbits and some of it bends away from our eyes. It was the absence that proved the presence. The image looked almost too perfect, like a simulation, like an artist's interpretation. But it was built from real data, from real radio waves captured around the globe and stitched together with the precision of global timing. The result was not just a picture, it was confirmation, a silhouette of something that can't emit light, made visible by how it curves the very structure of the universe. And more recently, we've done the same for Sagittarius A star. Though more challenging, because of its smaller size and faster variability, the image carries the same signature. A dark centre surrounded by light, shaped not by brightness, but by gravity. In both cases, what we see is not the black hole, but the stage around it. We see what the black hole has done to space, and to light, and to time, and from that, we reconstruct its presence. It's a bit like walking into a silent room and noticing that all the chairs point to one spot. There's no speaker, no voice, no figure on the stage, but the arrangement tells you something is there, something everyone is facing, something silent but central. That's how we see black holes. We trace their influence. We measure the spin of stars that orbit invisibly. We observe the flickering of gas just before it disappears. We follow beams of particles back to their source and find only absence. We map the distortions in galaxies that lie behind them. We chart the faint X-rays of accretion. We listen to the chirps of gravitational waves. And from this patchwork of clues, we know. And perhaps that's the most beautiful part, that something so silent, so hidden, can still be known. Not by light, but by consequence. Not by presence, but by gravity. That in a universe built on motion and mass and energy, even the invisible leaves a mark, a tug, a trail, a story. At the heart of nearly every large galaxy we've ever observed, there sits something massive, something quiet, something that, like the calm eye of a hurricane, holds everything else in motion. These are the supermassive black holes, millions, sometimes billions of times the mass of our sun, and yet, for all their size, for all their influence, they are among the most mysterious objects in the universe. Not because we don't know they exist, but because we still don't fully understand why they do. Our own galaxy, the Milky Way, holds such a presence at its core. Sagittarius, a star. A black hole roughly 4 million solar masses in weight. It's modest by galactic standards. Others dwarf it entirely. The black hole in the galaxy M87, for instance, the one whose silhouette was captured by the Event Horizon Telescope, is over 6 billion solar masses. And then there are quasars, those ancient beacons from the early universe, whose central engines may harbour black holes tens of billions of times the sun's mass, swallowing matter at rates that would make even stars seem fleeting. But how did they grow so large? That is the heart of the puzzle. One possibility is simple, at least in theory. They started small and grew steadily over time, consuming gas, dust, stars, and even other black holes. But this explanation hits a snag when we look at the early universe. We see quasars, fully formed, brilliant, supermassive black holes, less than 1 billion years after the Big Bang, and in cosmic terms that's barely enough time to build a galaxy, let alone raise a black hole from stellar infancy to supermassive adulthood. So maybe they didn't start small. Maybe in the early, dense universe, conditions allowed for direct collapse. Huge clouds of gas falling inward so quickly, so completely, that they bypassed the usual star-forming phase and collapsed directly into massive black hole seeds. These seeds, perhaps 10,000 or 100,000 times the mass of the Sun, would have had a significant head start, and under the right conditions they could grow rapidly, fed by the turbulent environment of newborn galaxies. But this raises another question. Did the black holes form inside galaxies, or did galaxies form around the black holes? It's a cosmic chicken and egg problem. When we look at galaxies today, we find a strong correlation between the mass of the central black hole and the properties of the galaxy's bulge, its stars, its density, its structure. This relationship, known as the M-sigma relation, is too tight to be coincidence. It suggests a deep link between the growth of the black hole and the growth of the galaxy itself. Somehow, across billions of years, as stars formed and dust settled and spiral arms stretched out, the black hole at the centre kept pace, growing in tandem, influencing and being influenced, and yet the mechanism is subtle. Black holes are small compared to galaxies. Sagittarius, a star for all its mass, is just a speck in the grand scale of the Milky Way. Its gravitational reach extends only a few light years before it's overtaken by the collective pull of the galaxy's stars, and yet it seems to know what the galaxy is doing, or perhaps the galaxy knows what it's doing. The feedback between the two is still being unravelled. One idea is that the black hole exerts influence not through direct gravity, but through energy. When gas falls in, it heats up, glows, and sometimes gets blasted outward in enormous jets. These outflows can sweep through the galaxy, pushing gas away, suppressing star formation, or triggering it in other regions. It's like a heart that doesn't control the limbs directly but pumps blood that shapes their motion. A central engine whose breath stirs the spiral arms. And sometimes that engine flickers. Sagittarius. A star today is quiet, dormant compared to its active cousins, but we know it wasn't always so. Observations of nearby gas clouds and X-ray echoes from surrounding dust suggest that, in the not-too-distant past, maybe just a few million years ago, our central black hole flared, briefly, powerfully. It may have consumed a passing star or a blob of gas, and when it did, it lit up, its jets and radiation sweeping across the galactic core. The echoes of that moment still shimmer around us. This suggests that black holes are not static. They go through phases, active and quiet, fed and starving, luminous and dark. Their stories are not just about gravity, but about hunger, about influence, about timing. They wait, mostly, but when the moment comes, they feed. And when they feed, they shape their world. Which brings us to one last idea. Maybe galaxies need black holes. Not just as a side effect, not just as an ornament in the centre, but as a kind of anchor, a gravitational and energetic core that helps organise the chaos of stars and dust. Maybe without black holes, galaxies wouldn't form the way they do. Maybe they'd sprawl instead of spiral, drift instead of coalesce. Maybe in some quiet way, black holes give structure to the universe, not by being loud, but by being there, steady, constant, waiting. And if that's true, then these invisible giants are not accidents. They're architects. Silent ones, yes, but essential. We don't know the full story yet. We may never know it completely. But every orbit we track, every shadow we image, every distant quasar we measure, it all brings us closer, not just to understanding black holes, but to understanding why the universe looks the way it does, why it holds together, why we're here, orbiting a star in a galaxy that orbits a centre around a black hole that hums quietly in the dark. Long before the first galaxies had spiraled into shape, before the first stars burned hot and fierce in the darkness, before even atoms had properly come together, there may have been black holes, not vast ones, born of stellar deaths, not supermassive ones at galactic hearts, but tiny ones, fleeting ones, ancient ones, perhaps the first to ever exist. These are known as primordial black holes, hypothetical remnants from the earliest moments of the universe, and if they're real, they might hold answers to some of the most persistent cosmic questions we've ever asked. To understand them, we need to travel far back, not just in space, but in time, all the way to the first fraction of a second after the Big Bang. In that brief, chaotic window, the universe was not as we know it. It was not filled with galaxies, stars, or even light in the usual sense. It was a seething quantum froth, hot beyond imagination, dense beyond comprehension, expanding faster than anything today. And within that early soup, fluctuations danced. Not all regions were created equal. Some were just slightly denser than others, slightly more curved, slightly more prone to collapse. Most of these fluctuations smoothed out over time, stretching with the expansion, cooling into the seeds of galaxies. But some, according to theory, may have collapsed immediately, their density too high, their gravity too strong. The result? Tiny black holes, formed not from dying stars but from the raw conditions of the Big Bang itself. These are the primordial black holes, objects that could be as small as a mountain, as light as an asteroid, or in some versions, even smaller than a grain of sand. And because they formed so early, they've had more time than anything else in the universe to shape what came after. But do they exist? That's the puzzle. No one has seen one. Not directly, not yet. But their existence would explain many things. Perhaps even too many. For one, they're a candidate for dark matter. Dark matter is one of modern science's great unknowns. We know it's there. Its gravity shapes galaxies. Its presence bends light. Its mass anchors cosmic structures. But we don't know what it is. It doesn't shine. It doesn't absorb. It doesn't react in any way that normal matter does. It simply pulls. It has mass but no voice. Primordial black holes, being dark, massive and long-lived, fit that description. If enough of them were scattered throughout the universe, they could account for the missing mass. Not some exotic particle or undiscovered force, just black holes, left over from the beginning. Too small to collapse, stars too quiet to light up space, but numerous enough to leave a gravitational fingerprint. It's an elegant idea, and one that scientists have been testing. They've looked for microlensing events, moments when a black hole passes in front of a distant star and bends its light, like a magnifying glass. They've searched the cosmic microwave background for the subtle effects of early black holes heating gas. They've scanned gamma-ray skies, seeking the final moments of tiny black holes evaporating into light. Because yes, if primordial black holes are small enough, they should evaporate. That prediction comes from Stephen Hawking, who, in the 1970s, showed that black holes are not perfectly black. Quantum effects near the event horizon allow for particle-antiparticle pairs to form and separate. One falls in, the other escapes. To a distant observer, the black hole appears to radiate, very slowly, very faintly, over unimaginable timescales. This process, now called Hawking radiation, means that small black holes lose mass, and the smaller they are, the faster they evaporate. A stellar mass black hole would take longer than the age of the universe to evaporate, but a tiny one, a primordial black hole perhaps, might just now be reaching its final breath, its last flicker, a burst of energy that could in theory be detected. If we ever saw one, it would be a message from the beginning, but so far no such burst has been found. No microlensing curve has clearly pointed to a primordial black hole. No radio wave, no infrared echo, no particle stream. If they're out there, they are hiding well. Still, the idea refuses to fade, because if primordial black holes exist, they offer not just an answer to dark matter, but a bridge between the quantum and the cosmic. They would be the only objects shaped entirely by the conditions of the Big Bang, neither built from matter nor forged in stars. They would be fossils of an earlier physics, snapshots of what the universe was before the rules we know had settled into place. And there's something quietly beautiful in that. That the oldest things in existence might be the darkest. That some of the smallest may hold the memory of everything. That even in silence, even in absence, the early universe may have left behind pieces of itself, not in light, not in dust, but in gravity. It's possible they no longer exist, that they evaporated long ago, that their stories ended before the first galaxies even began to form. But even so, their absence is instructive. It tells us what the early universe could or could not produce. It narrows the paths, it sharpens the map, and every non-detection brings us closer to understanding what dark matter is not, which in turn brings us closer to understanding what it might be. So perhaps, as you rest tonight, you can imagine them, not as monsters or mysteries, but as ancient embers, seeds of collapse born from chaos, tiny, quiet witnesses to a universe still figuring itself out. If they are there, they're still orbiting, still moving unseen between the stars, and if not, their ghost remains, in the equations, in the sky, in the gentle whisper that maybe, just maybe, the beginning left behind more than we thought. Once, the idea of two black holes merging was an elegant prediction, mathematically neat, theoretically possible, but far beyond our reach. It was a ghostly calculation scribbled into relativity's margins, a hypothetical performance too quiet to ever be heard. But then we listened, and the universe answered. The first detection came in 2015, when LIGO, the Laser Interferometer Gravitational Wave Observatory, measured something unprecedented, a tiny ripple in space-time that passed through Earth. For a fraction of a second, space itself stretched and contracted by less than 1,000th of the width of a proton. It was barely there, a passing tremble. But in that moment, humanity had heard something no ear was built to hear. The final cry of two colliding black holes, more than 1 billion light-years away. Since that first whisper, the catalogue has grown. LIGO and its European partner, Virgo, have detected dozens of such events. Each one is a story. Two black holes, orbiting invisibly for eons, finally coming together in a moment of shared gravity. Some are small, just a few times the mass of our Sun. Others are large, even unexpectedly so, forming black holes heavier than we thought possible through normal stellar collapse. Some have near equal partners, dancing in symmetry. Others show stark differences, suggesting chaotic formation histories or chance meetings in crowded stellar nurseries. Together, they form a quiet archive, a gravitational library of events that occurred long before Earth took shape, whose echoes only now reach us across the void. And with each new detection, patterns begin to emerge. The masses of black holes, for example, reveal subtle boundaries. There seems to be a mass gap, a region where, strangely, black holes are scarce. Below around 2.5 solar masses, we find neutron stars, the dense cores left behind when smaller stars die. Above about 5 solar masses, we begin to see black holes. But between these two values, nature seems to hesitate. Why this gap exists is still a question. It could be a product of how supernovae unfold, or something deeper. A rule of collapse written into the laws of physics themselves. Even stranger is the possibility of intermediate mass black holes, objects weighing in at hundreds or even thousands of solar masses, too heavy to come from a single star's death, too light to be the behemoths in galactic centres. If these exist, and some gravitational wave data suggests they might, they could be ancient relics, stepping stones on the way to the giants we see today. And then there are the spins. When two black holes merge, the spins of each body, how fast and in what direction they rotate, combine to affect the final product. By analysing the resulting waveform, scientists can infer whether the black holes were spinning in sync with their orbit, or chaotically, or not at all. These orientations provide subtle clues about their origins. If the spins are aligned, it suggests the black holes may have formed together, perhaps as a binary pair of massive stars. Their lives would have been intertwined from the beginning, evolving in tandem, collapsing into black holes still in orbit. But if the spins are misaligned, if one spins one way and the other another, it could indicate they formed separately, maybe in a dense star cluster where chance brought them together later in life. The difference matters because it tells us about how black holes live, whether they're born into pairs or meet as wanderers, whether the universe is neat and predictable or wild and full of collisions, and perhaps it tells us something about ourselves, about how structure arises not just from planning, but from chance, from dance, from proximity. We've also begun to detect systems that might merge again, triple systems, hierarchical setups where black holes are not alone, but part of more complex configurations. The gravitational waves from these could be even more nuanced, their signals modulated by third companions or orbital drift. These are harder to catch, but they're out there, waiting for our detectors to become even more sensitive. And they will. The next generation of gravitational wave observatories, LISA in space, the Einstein Telescope in Europe, Cosmic Explorer in the United States, will listen at lower frequencies for longer events over greater distances. They'll detect not just black hole mergers, but white dwarf interactions, neutron star spirals, and perhaps even the primordial waves left over from the earliest seconds after the Big Bang. But even now, with the tools we have, we're learning something profound. We are mapping a hidden sky, not of stars, but of motions, not of light, but of curves in space-time. A sky that has always existed, but only now begins to shimmer in our understanding. Each merger is a point in that map. A data point, yes, but also a story. A signal of gravity speaking across time. A line in the quiet poem of the universe. It's not unlike discovering a new sense. For thousands of years, astronomy was visual. We charted the heavens by their light. We named constellations, measured brightness, painted orbits in ink and memory. But now, we also listen. The universe no longer just shines, it sings. And with each passing year, the harmony becomes clearer. And still, there are so many questions. Why do some black holes form in pairs, while others remain alone? Why do some spin madly, while others seem still? Why do masses clump in some places, vanish in others? What happened in the early universe to shape this invisible landscape? How many more mergers are out there, whispering past us, too quiet to hear? For now, we do not know all the answers, but we know this. We're not at the centre of the universe, but we're at the centre of a moment when the dark has begun to reveal its shape, when absence has become signal, when black holes, long thought to be the ultimate silence, have turned out to be storytellers. Reluctant, yes, but eloquent. Their language is gravity, and we're just beginning to learn how to read it. We often think of black holes as eternal. Once formed, we imagine them locked in their silence forever, unchanging, patient, endless. And for a long time, that's exactly what science believed. In Einstein's universe, a black hole was the ultimate conclusion. Mass collapsed into itself, cut off from the rest of space by its own gravity, never to change again except by consuming more. It was a one-way journey into stillness. But in the 1970s, Stephen Hawking, working at the intersection of general relativity and quantum theory, found something unexpected, something quietly profound. According to his calculations, black holes glow, not in the way stars glow, not with visible light or warmth, but with something even stranger. Radiation that emerges from the very edge of a black hole's event horizon, the place where time slows, where escape becomes impossible, where light itself bends into silence. From that boundary, according to Hawking, there seeps a faint, slow, subtle shimmer. To understand why, we must first imagine a vacuum, not as emptiness, but as possibility. In the quantum world, a vacuum is not blank. It is a restless canvas where particle-antiparticle pairs constantly blink into and out of existence. For a fleeting moment, a pair appears, one positive, one negative. They cancel each other out almost immediately, returning to the silence of the vacuum, leaving no trace. But near the edge of a black hole, something curious happens. If such a pair forms right at the event horizon, one particle might fall in, trapped forever, while the other escapes. The universe, strict in its accounting, doesn't let that slide. Energy has to come from somewhere. And so, the black hole loses a tiny bit of mass to pay the cost of that escaping particle. It is a debt paid in whispers over cosmic timescales. This process, Hawking radiation, is extraordinarily slow. For a black hole the mass of a star, the rate of evaporation is negligible. It would take longer than the current age of the universe to noticeably shrink. But over time, billions, trillions, perhaps even more, the black hole will lose mass, bit by bit, until eventually it vanishes. The final moments would be fast and bright in theory. As the black hole becomes smaller, the rate of radiation increases, its temperature rises, the glow becomes more intense, and then, gone, a quiet death. The end of gravity's most private secret. We have not yet observed this process. Not directly. No telescope has seen a black hole evaporate, but the mathematics is compelling. It brings together two great frameworks of physics, relativity and quantum theory. It gives black holes a lifespan, a direction in time, a kind of vulnerability, and perhaps, strangely, a kind of grace. Because what Hawking's insight reveals is that even the darkest objects in the cosmos are not exempt from change. They too feel the passage of time, not in days or centuries, but in the slow, patient erosion of mass into radiation. They do not last forever. Nothing does, not stars, not galaxies, not even the silence between them. In this there is something almost human. We age, we change, we radiate energy, heat, thought, presence. We leave behind echoes, and so do black holes in their own way. Not noise, not memory, but particles. Tiny messengers released to the universe, traces of what once was. It's comforting, perhaps, to imagine that even black holes are not immune to impermanence, that they too participate in the great unfolding, that they do not hold their secrets forever, but slowly let them go, that they begin as giants and end as whispers. There's also something quietly poetic in the idea that black holes die not with explosions, not with thunder or collapse, but with radiation, with light, with the very thing they once devoured. Imagine it, a black hole, born in violence, spending eons in stillness, and then, over untold ages, growing fainter, smaller, until finally, in a moment that passes without sound, it disappears. A soft final breath into the dark, and what remains? The radiation, perhaps, the energy it released, the imprint it left on the universe, the slight curve it gave to space while it lived, and maybe, just maybe, the information it once held. A question we'll explore next. But for now, we sit with this image. A black hole, once thought eternal, slowly fading from the universe like mist from a quiet lake at dawn. It changes how we think about endings, because if even black holes die, then all things move, all things rest, even the strongest give way, eventually. Not with despair, but with stillness. Not with regret, but with inevitability. And in that inevitability there is a kind of beauty. The universe doesn't erase, it transforms. So when you think of black holes, don't think only of darkness. Think of the quiet light they may one day become, the slow surrender of mass to time, the glow that begins where we thought nothing could escape. That's Hawking's gift to us, a reminder that mystery doesn't mean permanence, and that even the deepest silence can hum with possibility. Let that be your thought as the night deepens, that even what cannot be seen can still shine. For a long time, science believed the universe played fair, that while things may burn, break or scatter, the underlying information, the raw ingredients of reality, was never truly lost. It could be scrambled, it could be transformed. But it was still there, hidden in the echoes. The principle comes from quantum mechanics, that the wave function of a system, which contains everything there is to know about it, evolves in a way that's fundamentally reversible. Unwind the clock, and you should, in theory, be able to reconstruct the past. But black holes challenge that comfort. Because if Hawking radiation is real, and if black holes slowly evaporate into nothing over unimaginable spans of time, then what happens to the information that fell in? What becomes of the atoms and photons, the electric charges and quantum spins, the intricate dance of particles that once crossed the event horizon and disappeared into the silence? Do they vanish? Hawking's original calculations seemed to say yes. The radiation, according to the math, was thermal, featureless, random, carrying no trace of what had gone in. It was like ashes from a fire that revealed nothing of the pages they once were. The implications were staggering. It meant the universe could forget. That black holes weren't just prisons for matter and light, but for information itself. And when they vanished, so did the memory of everything they had consumed. This idea, called the information paradox, shook physics to its foundation, because if information can be lost in black holes, it might be lost elsewhere. And if it can be lost, then quantum mechanics, one of the most successful theories in all of science, is incomplete, or even wrong. But physicists are a persistent kind. They began looking for loopholes. Maybe the information escaped somehow. Maybe the radiation isn't truly random, but subtly encoded. Maybe, if you had perfect detectors and infinite patience, you could reconstruct everything that ever fell in. Not through direct reversal, but through pattern. The tiniest imprints in the radiation, whispered out over time. It would be unimaginably difficult, but not impossible. Not forbidden. Others turned to the event horizon itself. Some proposed that information clings to the edge, that it's stored on the surface like patterns on a drumhead. This led to the idea of the holographic principle, a strange but beautiful proposal that the entire content of a volume of space could be described by information encoded on its boundary. Like a three-dimensional movie projected from a two-dimensional film. In this view, a black hole is not just a thing that swallows, but a surface that remembers. It's poetic in its way. A boundary that holds all that has passed, a skin stretched with memory, a veil between what falls in and what remains known. This idea gained strength in string theory, which sees particles not as points, but as tiny, vibrating strings in many dimensions. Within that framework, theorists began to calculate black hole entropy, the measure of how many ways a black hole could be configured internally. And to their amazement, it matched what Hawking had predicted, if they assumed the information lived on the surface. That changed everything. Hawking himself revised his stance in later years, suggesting that perhaps information wasn't lost after all, but that we hadn't yet found the right mathematical language to see it. Others proposed more radical ideas, like firewalls, energetic boundaries that destroy information at the event horizon to preserve the consistency of physics. But these come at a cost. They violate the peaceful nature of black holes predicted by relativity, and so remain controversial. The truth is, we don't yet know, not fully, not confidently. We're standing at the edge of two great theories, relativity and quantum mechanics, and in black holes they collide. One describes smooth curves and the warping of space, the other deals in probabilities and entanglement. Both are right, in their domains, but together, in the heart of a black hole, they disagree. That disagreement is not failure, it's opportunity. Because somewhere in the resolution of the information paradox lies the next great step in physics, a unified theory, a deeper truth that doesn't choose between gravity and quantum law, but shows how they are one. It might involve new mathematics, it might demand new dimensions, it might ask us to abandon ideas we've held dear for a century, but it will come. Science moves forward by asking better questions. And few questions are better than this. Does the universe forget? Because if it doesn't, then everything matters. Every atom, every moment, every pattern. Nothing is truly erased. The past is not gone. It's just woven deeply into the fabric of what is. And even a black hole, with all its mystery and silence, becomes a chapter, not a shredder. If it does forget, then we must ask why. What is it about a black hole that unravels the rules? Why does silence have such power? Both answers lead to beauty. If the universe remembers, then we live in a cosmos of perfect continuity, a place where no detail is wasted, no story discarded. If it forgets, then we dwell in a world of transformation, where endings are real and final, and where mystery carries weight. Either way, we're surrounded by meaning. So let the paradox remain, for now. Not as a flaw, but as a doorway. A place where our knowledge reaches its edge, and something deeper begins. And let that be comforting. Not everything needs resolution. Some questions are better when they stay open, like windows at night, letting in the stars. And perhaps, as you rest, you can think of the information paradox not as a riddle to solve, but as a lullaby from the cosmos. A reminder that not even black holes are finished stories. So, here we are, at the edge of it all. After a journey through birth and collapse, through silence and collision, through light that bends and time that slows, we come to the last shadow. The one that does not move or shine. The one that waits, not with menace, but with stillness. A shadow shaped not by absence, but by presence so complete, so dense, so quietly firm that it curves the world around it like a hand resting on soft cloth. A black hole. You began this journey perhaps picturing it as a monster, as something strange and far away, something that devours and disappears. But now, maybe it feels different. Not less powerful, but more gentle. Not less mysterious, but somehow more familiar. Because a black hole is not a hole at all. It's not emptiness. It's not a thing that rips or breaks or sucks. It is gravity resting. It is space drawn inward, folded carefully by mass. It is time, slowed into something soft. It is a place where what we know pauses, and what we feel begins to glow. Think of how we've come to know them, not by seeing, but by listening. Not by touching, but by watching others move around them. Stars that orbit, light that bends, whispers in space-time that travel for 1 billion years to reach us. Black holes never call attention to themselves, but everything around them tells their story, and in that way, they are a lot like many things in life. Some of the most powerful forces we know, love, memory, gravity, silence, do not shout. They do not sparkle. They move quietly, but with weight. They shape us without needing to be seen. And sometimes they only reveal themselves through their effects. The way a path curves, the way a voice softens, the way a star chooses to move. Black holes are that kind of story. One told not with light, but with curve. Not with noise, but with rhythm. Not with answers, but with presence. And maybe that's why we find them so compelling. Because in their mystery, we hear echoes of our own. We too are made of stars that collapsed. We too move in orbits shaped by forces we don't always understand. We too hold inside us things that cannot be seen. Memories, questions, hopes that bend the shape of our days. So sleep now, little shadow. Not because the journey is over, but because you have found a quiet place in it. You are not a monster. You are not a threat. You are the pause between thoughts, the breath between stars, the point where even time sighs and rests its head. You remind us that the universe is not in a hurry, that some stories unfold slowly, that even in collapse there can be grace, that silence is not the opposite of knowledge, but its threshold. That mystery is not always something to solve. Sometimes it is something to hold, like a smooth stone in your hand, heavy and cool and real. You remind us that our questions are not failures, that the limits of our knowledge are not fences but gateways, that to not know is to be alive, and that the most beautiful parts of existence are often the ones we cannot explain, not yet, and maybe not ever. And so, dear listener, wherever you are, however this night finds you, know this: you are part of the same universe that forged these quiet giants. You are made of the same particles, shaped by the same gravity, bathed in the same light that circles the edges of what can't be seen. You're not separate from the cosmos. You're a chapter in it, a ripple in its silence, a warmth in its night. Maybe that's why we search the stars, not to escape Earth, but to find reflections of ourselves in the dark, to see our curiosity written across the sky, to feel small, not in fear, but in wonder. Because in being small, we become part of something vast, something soft and slow and impossibly old. A black hole may sit at the centre of our galaxy, but it is not alone. It is surrounded by stars, by light, by memory and motion, just like you. So rest now in the gravity of everything. Let the stars spiral gently above you. Let the silence carry you. Let the questions remain unanswered but not unloved. Let the shadow tuck you in, not as something to fear, but as something that makes the light around it more precious. And tomorrow, when you wake, the black holes will still be there, curving time, holding galaxies, waiting patiently in the deep. They won't mind if you fall asleep before the ending. They've been here long enough to know every story, like every star, must fade eventually. But for now, there is still time, there is still breath, there is still the soft pull of gravity and the gentle whisper of things we cannot see, but feel. Sleep well, little ripple in the dark. You're part of it all, and it is at peace.